99% of the energy used to create an X-ray is lost as heat. Only 1% becomes actual diagnostic photons. A modern clinical X-ray tube operates less like a standard camera and more like a high-powered, carefully controlled particle accelerator. The core architecture of this accelerator has remained remarkably consistent for over a century. You have a cathode and an anode, separated by a gap, sealed inside a glass vacuum envelope. Those early glass designs worked efficiently enough for low-power imaging, but scaling up the tube voltage to penetrate dense human tissue created a massive thermal bottleneck. Generating enough photons meant generating enough heat to melt the equipment. To see how modern medicine solves this, we have to track the exact physical mechanism of X-ray production, step by step, from electron extraction to subatomic collision. Radiologists must understand these exact mechanisms to predictably tune the resulting X-ray spectrum for varying patient densities. Harnessing diagnostic X-rays relies entirely on controlling and surviving an incredibly inefficient, destructive thermal event. The electron's journey begins at the cathode. A current passes through a thin tungsten filament, heating it to over 3,400 degrees Celsius. This imparts enough thermal energy to overcome the binding energy of the tungsten atoms, causing a cloud of electrons to boil off into the surrounding vacuum. This is thermionic emission. The filament current, measured in amperes, is the sole variable dictating the total number of electrons released into this cloud. Increase the current, and the cloud grows denser. But a static cloud of electrons is useless on its own. They need to strike the positively charged anode target across the gap. To pull them across, the machine applies an accelerating potential, or tube voltage, measured in kilovolts. This creates a steep negative to positive gradient. A standard alternating current wave, however, regularly drops back to zero. Drops in potential, or voltage ripple, produce slow-moving electrons. Those slow electrons yield weak, low-energy photons that cannot penetrate tissue. To fix this, the sinusoidal wave is rectified into a high-frequency square wave that stays constantly near the peak voltage. High-frequency generators are essential to supply this constant potential, ensuring the electrons hit the target with maximum velocity. Achieving a continuous high-velocity stream of electrons requires manipulating both the thermal state of the filament and the rectified electrical frequency of the generator. The accelerated electrons slam into their destination, the anode target. Because To survive the impact, the anode disk rotates rapidly, usually around 50 Hz, spreading the intense thermal load along a continuous circular focal track. This introduces the line focus principle. By placing a bevel on the rim of the spinning disk, the actual focal spot handling the heat is physically wide, but the effective focal spot projected down toward the patient remains sharply narrow. Decreasing the target angle creates a sharper focal spot for better image resolution, but it forces the X-rays on the anode side to travel through more of the target's physical material. This causes the beam intensity to drop significantly on that side, a phenomenon known as the anode heel effect. Clinicians use this asymmetry to their advantage. They position the more intense cathode side of the tube over the densest part of the patient's anatomy to compensate for the beam's uneven attenuation. The macroscopic geometry of the X-ray tube is a strict three-way compromise between heat dissipation, spatial resolution, and beam uniformity. If we push past the hardware and zoom into the surface of the target itself, we hit the heavy tungsten atoms. Here, 80% of the X-ray beam is created through an atomic interaction called Bremsstrahlung, or braking radiation. A bombarding electron speeds into the target and is attracted by the strong electric field of a tungsten nucleus. As it swerves sharply around the nucleus, it rapidly decelerates, shedding its lost kinetic energy as an X-ray photon. Because the incoming electrons swerve at completely unpredictable distances from the nuclei, they lose varying amounts of energy. This produces a continuous, wide-ranging spectrum of photon wavelengths. A secondary interaction, called characteristic radiation, produces the rest of the beam. Occasionally, a bombarding electron scores a direct hit, ejecting an inner shell electron entirely out of its orbit. An outer shell electron instantly drops down to fill the vacancy. That sudden drop in energy state emits a single distinct photon. This emitted photon has a precise, discrete energy value dictated entirely by the binding energies of the target material. For tungsten, the drop from the L shell to the K shell yields exactly 59.3 kiloelectron volts. The final raw X-ray beam is a mathematically predictable composite of these two distinct subatomic collision types. This is a chart showing the resulting X-ray energy spectrum. The smooth asymmetrical curve represents the continuous range of photons produced by Bremsstrahlung. The precise, discrete emissions of characteristic radiation interrupt that smooth curve as sharp vertical spikes at specific energy markers. The total area under the curve represents beam quantity, or intensity. The rightward position of the curve along the x-axis represents beam quality, or its ability to penetrate an object. Increasing the tube current, or MA, simply throws more electrons at the target. The curve grows taller, increasing the quantity of photons, but the minimum, maximum, and characteristic peak energies remain strictly locked in place. If the manufacturer increases the atomic number of the target material, the continuous curve grows, and those sharp characteristic spikes shift to the right, reflecting the target's higher discrete binding energies. Manipulating tube current or target material alters the volume of photons and specific resonance peaks, but it does not grant the operator control over the maximum penetrability of the beam. The most powerful operator control for altering beam quality is the tube potential, or kV. Increasing the kV increases the total quantity of photons, but it also physically pulls the maximum and average energy strictly to the right. Once the kV crosses the critical binding energy threshold, it triggers those characteristic spikes. Yet, even at high kV, the raw spectrum holds a critical flaw, a massive cluster of low-energy photons occupying the far left of the curve. These soft X-rays do not have the energy required to pass through the patient to the detector. They are entirely absorbed by the tissue, contributing to harmful, redundant radiation dose without adding any value to the image. In early radiology, patients were exposed to this unshielded, unfiltered raw beam directly. Today, operators use beam filtration. Placing a physical metal window at the tube's exit intercepts the beam before it hits the patient. Look at what this filter does to the spectrum geometry. The left side of the curve is effectively chopped off. By eliminating those low-energy photons, the total number drops, but the average energy of the remaining beam shifts significantly higher. The modern X-ray tube is a precisely tuned particle accelerator. Through mastery of thermionic emission, using high-voltage physics and selective filtration, radiologists sculpt a chaotic thermal event into a perfectly calibrated diagnostic tool.